The first spacecraft bound for Mars are scheduled to launch in 2026, and if everything goes according to plan, the first crewed flights will follow in 2028. For the first time in our history, human beings will become a multi-planetary species. But before any of that can happen, we have to solve the first enormous problem, getting off the Earth in the first place. And that comes down to one critical challenge: burning as little fuel as possible in the process. Most of the energy in any trip to Mars gets spent right at the start, breaking free of Earth's gravity. Once a spacecraft reaches open space, there's no air resistance to fight against, so as long as it's pointed in the right direction, momentum alone will carry it the rest of the way. Stopping at the Moon to refuel might sound practical, but it isn't. Landing on the Moon and then taking off again would burn more fuel than simply flying straight to Mars. So the logic that actually makes sense looks like this. A Mars-bound rocket launches and uses the bulk of its fuel just to escape Earth's gravity. Once it reaches low Earth orbit, a second vehicle, fully loaded with propellant, docks with it to top off the tank before the real journey begins. So how often can we actually launch toward the red planet? Earth takes 1 year to circle the Sun, while Mars takes almost 2, closer to 23 months. That means the two planets line up in a favorable position roughly every 26 months. That's exactly why 2026 is the target for the first uncrewed test flight to Mars, with the first human crews following in 2028. The length of the trip itself depends on how quickly Starship can accelerate and decelerate, but based on the technology available right now, each leg of the journey should take around 6 months. That timeline is also the reason SpaceX plans to send at least 5 separate spacecraft on each Mars transfer window. None of this would be economically realistic without Starship. Back in the 1980s, launching a single kilogram into space aboard a major rocket cost more than $50,000. The space shuttle chipped away at that cost gradually, but it really was gradual. Then SpaceX entered the picture, and within about 15 years, the cost per kilogram dropped from around $12,000 to roughly $3,000. About 375 times cheaper than the space shuttle era. Even so, building a Martian city capable of growing without constant resupply from Earth would require at least 1 million tons of equipment and material, which would cost more than $1,000 trillion. An obviously impossible figure, given that the entire GDP of the United States sits at around $29 trillion. But if launch costs could fall by roughly a factor of 1,000, the total price tag for a sustainable multi-planetary civilization would shrink to about $1 trillion. A cost that could be spread across 40 years, working out to roughly $25 billion annually. With departure fully mapped out, there's another massive challenge waiting on the other end, actually landing on Mars. Unlike Earth, Mars has an incredibly thin atmosphere, barely 1% as dense as ours, which means atmospheric drag alone can't be relied on to slow a spacecraft down the way it can here. And when you're traveling faster than 20,000 kilometers per hour, your braking plan had better work flawlessly, because any mistake turns your spacecraft into the most expensive meteorite in history. To solve this, SpaceX designed a maneuver nicknamed the belly flop, borrowed from the pool diving move where you slam into the water stomach first. Mimicking that same idea, the spacecraft turns sideways as it enters the Martian atmosphere, using its entire body as an aerodynamic brake to maximize drag and cut speed dramatically. Only once it's close to the ground does Starship flip into a vertical position, firing its engines for a controlled, powered descent. Next comes the challenge of finding somewhere safe to actually land. Mars is covered in craters, boulders, and treacherous slopes, and the last thing anyone wants is to add to that crater count. Obviously, any landing site will need to be flat, but surviving there long-term matters just as much as touching down safely. So what makes a location genuinely suitable for a Mars settlement? 3 main factors decide that: access to essential resources, favorable climate conditions, and the potential for future expansion. First, access to water. On Mars, there are no rivers or lakes. Water exists mainly as ice buried beneath the surface or locked into the polar ice caps. That ice sits under a layer of dust and rock, which shields it from the planet's brutal surface conditions. Reaching it will require excavation, since water isn't just essential for drinking. It's also key to producing oxygen and rocket fuel, something we'll get into shortly. It's also critical that this ice sit close enough to the surface to be reached practically, ideally within about 16 feet or 5 meters of the top layer. Second, strong sunlight exposure. That's why the best candidate locations sit relatively close to the equator, at latitudes below 40 degrees, where sunlight is more abundant and temperatures are somewhat less extreme, though still around -60 degrees. That combination makes power generation and habitat maintenance far more manageable. Martian dust storms are also a serious concern, so ideal sites need to balance strong solar exposure against a lower risk of dust accumulation to keep energy production reliable. Third, geological safety. Landing on a flat plain doesn't just make descent easier, it also reduces the danger of unstable slopes and helps avoid regions with recent geological activity or fresh impact craters. The best locations sit at relatively low elevation, ideally between roughly 2 and 2.5 miles below the reference elevation, or about 3 to 4 kilometers. At those depths, the atmosphere is slightly denser, which improves landing conditions, moderates temperature swings, and makes it easier to capture carbon dioxide, a resource essential for producing both oxygen and fuel. Combine all three criteria, and one location stands out clearly. A basic map of Mars doesn't reveal much at first glance, but a topographic version, where red marks higher elevation and blue marks lower ground, makes the best candidate regions much easier to spot. One of the most promising sites scientists have identified is Arcadia Planitia, sitting at an elevation of roughly -4 kilometers and a latitude of about 40 degrees. It stands out for being remarkably flat and safe, while also showing strong signs of accessible underground ice. With a landing site chosen, the next hurdle is pure logistics. In 2026, 5 uncrewed cargo ships will be sent to Mars with one primary mission, confirming that water is actually present and reachable, while also identifying any hazards in the terrain. Beyond that, these same ships will be responsible for deploying power systems, mining equipment, and life support infrastructure that will already be waiting when the first astronauts arrive. That brings us to 2028, when at least 2 crewed vehicles and 2 additional cargo ships carrying further equipment and supplies are scheduled to arrive. If serious problems come up along the way, the crewed missions could be delayed by another 2 years. One of the very first tasks for these early settlers will be building a fuel production plant that converts Martian water and carbon dioxide into the methane and oxygen the return ships will need. They'll also need to construct an initial base capable of serving as a foundation for future growth, with the ultimate goal of becoming a fully self-sufficient city as quickly as possible. So how would that future base actually take shape? SpaceX envisions the growth of a Martian city unfolding across 4 broad phases. The earliest phase would look like little more than a scattered handful of structures. A bit later, the base would grow into something closer to a mid-sized settlement. By the 3rd phase, it would resemble a small colony in its own right. And in the 4th and final phase, the Martian city would be complete. And, at last, fully self-sufficient. But getting there depends on solving 8 critical challenges: power, oxygen, water, food, radiation, dust, infrastructure, and population. Let's start with that last one. SpaceX's stated goal is reaching a population of 1 million people within 2 or 3 decades. Naturally, that growth would happen gradually. In the earliest stages, only a small group of highly specialized workers would be sent to handle the base's initial construction. Given the risks tied to early colonization, these workers would likely receive substantial compensation from the organizations sending them. But as the settlement expands and comes to be seen as reasonably safe, later arrivals might have to cover their own costs to travel to Mars, whether out of pocket, through work contracts designed to offset expenses, or through loans. The health of the Martian population is likely to be one of the most complex challenges of all, since simply living on Mars exposes settlers to conditions that affect both physical and mental well-being. One of the most immediate issues will be adapting to Martian gravity, which sits at only 38% of Earth's. Over the long term, that could lead to bone density loss, muscle atrophy, and cardiovascular problems, meaning colonists will need intensive exercise routines, habitats with simulated gravity, and specialized medical treatment. Then there's the psychological side. Settlers will find themselves roughly 140 million miles, about 225 million kilometers, From home, with communication delays ranging anywhere from 3 to 22 minutes depending on the planet's relative positions, combined with the total absence of Earth's natural stimuli, open skies, weather, familiar landscapes. This could easily produce stress, anxiety, depression, or even social friction within the colony. Addressing that will require pleasant communal spaces, recreational activities, and access to psychological support. Radiation presents another major health challenge. Without a meaningful magnetic field or a thick atmosphere, Mars offers virtually no protection from solar and cosmic radiation. On average, radiation levels on the Martian surface run about 50 times higher than on Earth, significantly raising the risk of cancer and other degenerative illnesses. To address this, both SpaceX and NASA are researching more advanced shielding for spacecraft and habitats alike. Down the road, artificial magnetic fields could potentially be used to deflect charged particles, loosely mimicking the protection Earth's own magnetic field provides. A simpler but equally effective option involves covering habitats with the planet's native dust, known as regolith, which functions as a natural radiation shield. A protective layer of water would help too, since water is remarkably effective at absorbing radiation particles. That same regolith I just mentioned is extremely fine, abrasive, and electrostatically charged, which makes it cling stubbornly to surfaces and damage equipment. It also contains toxic perchlorates that can pose serious health risks if inhaled. Minimizing that danger will require advanced filtration systems, sealed suits, and strict protocols within any habitable areas. Regolith also cuts into the efficiency of our next major challenge: power. Solar energy is expected to be one of the primary electricity sources on Mars, but it's only about 40% as effective there as it is on Earth. And regolith kicked up during dust storms can coat solar panels, drastically reducing their output. These storms can last for weeks and blanket huge stretches of the planet. Dealing with that will require automated cleaning systems for solar arrays. Just as important will be diversifying energy sources to guarantee a steady, reliable supply, relying primarily on nuclear power, supplemented by wind power in certain locations where it makes sense. But we're forgetting something absolutely essential: oxygen. The Martian atmosphere doesn't contain nearly enough oxygen for humans to breathe, since it's made up almost entirely of carbon dioxide, which means oxygen will have to be manufactured artificially. Fortunately, this particular problem already has a working solution. NASA has developed a technology called MOXIE, a device that's already been successfully tested aboard the Perseverance rover, which has been operating on Mars since 2021. Here's how it works. MOXIE pulls carbon dioxide directly from the Martian atmosphere and heats it to roughly 800 degrees, splitting it into oxygen and carbon monoxide. The oxygen gets released into habitats to keep them breathable, while the carbon monoxide is repurposed to help produce methane, which, combined with oxygen, fuels Starship for the trip home. On top of that, any water available on Mars could be split through electrolysis into oxygen and hydrogen, with the hydrogen also playing a key role in methane production. Speaking of water, it's not just needed for drinking. It's also essential for producing oxygen and fuel, and for supporting agriculture and basic hygiene. Extracting the ice itself is where systems like Redwater come in, a proposed system designed to drill into and extract water from beneath the Martian surface. Technology like this wouldn't just solve a critical resource problem. It could also support important scientific exploration missions along the way. As for agriculture, growing food on a planet with no fertile soil, no rainfall, and an environment that's hostile in nearly every way will demand genuinely innovative, efficient solutions. One of the most realistic options involves greenhouses, either hydroponic systems, where plant roots grow directly in nutrient-enriched water, or aeroponic systems, where roots hang suspended in air and get misted with that same nutrient solution. These setups could be installed inside protected habitats using either artificial lighting or filtered natural sunlight to support plant growth. Over the long run, Martian regolith could potentially be chemically treated and converted into something resembling fertile Earth soil, which would significantly boost the colony's self-sufficiency. And beyond producing fresh food, Martian agriculture would also help recycle both air and water within the habitat. The last major piece of the puzzle is infrastructure. Before any colonists arrive, autonomous robots will prepare the ground, leveling terrain, piling regolith over habitats for insulation and radiation shielding, and setting up solar panels and other power systems. The earliest structures will be prefabricated back on Earth and shipped to Mars aboard cargo rockets. These will be designed to be modular and largely autonomous, capable of deploying themselves with minimal human intervention. As the colony grows, internal transportation systems, power stations, and storage facilities for water and food will become essential. This infrastructure will form the physical backbone of the city and enable its continued expansion. Martian regolith itself could play a major role here too. It can be compressed into building bricks or fed into advanced three-dimensional printers to construct structures directly on site, cutting down significantly on how much material needs to be shipped from Earth. One more critical piece of infrastructure is communication with Earth. Mars sits, on average, about 140 million miles, roughly 225 million kilometers, from our planet, meaning signals take around 12.5 minutes to travel in just one direction. That delay actually varies quite a bit. When the two planets are at their closest, it drops to just 3 minutes, while at their farthest, it can stretch to 22 minutes. To bridge that gap, SpaceX has proposed a project called MarsLink, essentially an adapted version of its Starlink satellite network. This constellation of satellites orbiting Mars would use advanced laser communication technology, initially transmitting data at around 4 megabits per second, with an eventual goal of surpassing 1 petabit per second. MarsLink would establish a constant communication bridge between the two planets, carrying images, scientific data, and essential transmissions back and forth. It would also provide reliable communication infrastructure for future missions and colonies across the Red Planet. We dream of Mars, but every dream comes with a price tag. Who's paying for it? And more importantly, what do we get in return? In the early stages, space agencies like NASA and the European Space Agency will likely shoulder part of the cost, driven by scientific and strategic value, while companies like SpaceX drive costs down through reusable rockets, mass production, and outside investment. Space tourism represents one of the clearest early revenue streams, whether through short trips to the Moon or longer journeys to Mars. The chance to explore deep space is bound to attract enormous interest. If people today pay small fortunes just to visit Antarctica, what wouldn't they pay for an actual Mars experience? At an estimated price of around $300,000 per person, roughly 50,000 travelers a year could generate around 15 billion euros in gross annual revenue. Not exactly a mass market yet, but a genuinely profitable starting point. The Moon, Mars, and nearby asteroids could all eventually serve as strategic sites for extracting valuable minerals like helium-3, platinum, rhodium, and ruthenium, materials essential to advanced industries. That said, current technological limitations and steep transportation costs mean this option is really only viable over the long haul. Mars could also spawn some genuinely unusual secondary markets. Everything from small Martian rock samples to time capsules, or even scattering human ashes on the planet's surface, turning the Red Planet into a powerful emotional touchstone for people back home. Further down the line, Mars could even support the sale of taxed land parcels and habitats, opening up an entirely new interplanetary real estate market. Beyond the economics, colonizing Mars is likely to trigger a technological leap forward on a scale comparable to what emerged from the two world wars. Even if the project never achieves complete self-sufficiency, the technologies developed just to survive on Mars could transform sustainability efforts